in today's class, and we will begin with, or rather we will take a relook at the concept of local maxima and minima of a function that we were discussing in the last lecture. So we have talked about various things related to a function and its behavior, like we have talked about analysis of the intervals of x in which a function is increasing or decreasing on the basis of the algebraic sign of its derivative. If dy by dx or the derivative of a function is positive in a certain region, then the function is increasing, and if it is negative, then the function is decreasing. And then we had also understood about domain range and global maxima and minima and local maxima and minima of a function. So we'll continue with that analysis today. Right. So local maxima or minima let's just quickly recap on that concept. So basically, if the graph of a function is such that it has a peak point and then later it has a dip point, or the function increases and then after some time decreases and then after some time again increases, then we say that at precisely the point where the function reaches a peak before it starts dropping again or before it starts decreasing again, if we draw a tangent at that point, we can see that the slope of the tangent will be 0. So such a point is called a point of local maxima. And similarly, if the function is decreasing, but it reaches a dip point and after that point, it again starts increasing. So a tangent drawn at that point will again have a 0 slope. So we will say that that is the point of local minimum. So if the function is increasing for x less than a, and the function is decreasing for x greater than a, but at x equal to a, the function has a peak, has a sort of a peak value, then we say that that is the point of local maxima. What we can also see in terms of slope of the function is that the derivative of the function or the slope of the tangent would be positive for a point less than a, negative at a point x greater than a, but the slope of the tangent becomes exactly 0 at x equal to a. So in other words, f prime x is positive for x less than a, negative for x greater than a, but the value of the derivative becomes 0 at the point of local maximum. Okay. So slope of tangent equals to 0 at the point of local maximum. Now similarly, if we also analyze the other point here, b, similar kind of thing is happening here, but the function is instead, it is decreasing at a point before b, and the function is again increasing. And precisely at x equal to b, the function has, you can say, a sort of a dip point, or what we call a point of local minima. So once again, what we mean in terms of derivative of the function is that if we look at the slope of tangent at any point just before B, it is a negative slope. And the slope of the tangent at any point after B, it is again a positive slope. But precisely at B, the slope is 0. So the behavior of the derivative is again like this, that f prime x is negative for x less than B, is positive for x greater than B. And precisely at the point B, the derivative is 0. So again, this is a condition for point of local minimum. Okay. Slope of tangent again equal to 0 at x equal to B, which is a point of local minima. So this is what we had looked at last time, and on the basis of this kind of analysis, the behavior of a function, we had understood how to find the local maxima and local minima for a given function if we don't know its graph from beforehand, right? Now today we will see a little bit ahead, like how to use some more advanced techniques in calculus to directly find local maxima and minima without all this analysis about the intervals in which the function is increasing and decreasing, etc. Okay, so this is all what we've seen before. This is just a recap of what we did towards the end of last lecture, so you need not write all this down. Now moving ahead, we'll see that first of all we'll define another type of operation related to rate of change, and we'll see how that operation is useful in analysis of local maxima and minima, and that is called second derivative. Okay, let's understand what this term means. Second derivative for a function. So literally the definition of second derivative is that it is the rate of change of the derivative. So second derivative means rate of change of the derivative of a function. So basically for a function y is equal to fx, the derivative, as we know, is nothing but the instantaneous rate of change, which is the differentiation operator applied on the function, which in short form we write as f prime x. So this is the derivative. Okay. Now the second derivative, the symbol for it is a special symbol. It is d2y by dx square. We read it as d2y by dx square, but basically it's like a d square y upon dx square kind of term. But what does this term mean? Basically, it means it is the rate of change of the derivative, or in other words, second derivative is differentiation applied on the derivative of the function, which in short form we call f double prime x. So this is the symbol for the second derivative, and this is how we find out the second derivative of a function. So as you note this down, let's quickly see an example of how to execute this. This is very simple basically. It's like we have to just differentiate the derivative itself. So for example, for a function, let's say y is equal to x cube, we know that derivative dy by dx is 3x square. Okay. Or we get the derivative by differentiating the function, which becomes 3x square. So therefore now the second derivative, okay, which we'll write with the symbol d square y by dx square, but that is basically nothing but the derivative of dy by dx. So we need to now substitute this derivative over here. So become derivative of 3x square, which will become 6x. So now this 6x term, this is the second derivative of the function y is equal to x. So it's nothing really difficult. It is just you're repeating the operation of differentiation twice, okay, in two layers, you can say. So just make a note of this definition of second derivative and this particular example. Uh, we will do some work on this, and then we'll come back to local maxima and minima and understand how this is useful in that sense, in the application of analysis of local maxima and minima. Okay, so let's look at another example. So let's say this time I have the function y is equal to x square minus x to the power 4 plus 2x. So find dy by dx and d2y by dx square. Okay. And secondly, find the value, okay, of the second derivative at the point x equal to 1. So you want to find the value of the second derivative at the point x equal to 1. Just quickly work this out, people. Just work out the value and send it to me on the text message. Okay. If there's any doubt in this first question or in the concept of second derivative, please let me know. You can unmute yourself and ask. Yes, Kirti, that's correct. Now, second derivative also.
So may I rejoin
Yes.
the meeting? I'm not able to send messages in the chat.
Beta, can you speak a little louder, please? Beta, couldn't hear you.
So may I rejoin the meeting? I'm not being able to send messages to you.
Yeah, you can rejoin. Yeah. Yeah, correct, Kirti. Correct, Ryan. Correct, Yash. Yash, all three answers are correct. Very good. Yes, Kirti, correct. Akmal, correct. Very good. So the second part's answer you should be getting as -10, all of you. Yes, very good. Correct. So let's quickly go step by step with this. So as you can see that for the function, this one, dy by dx, you have to just differentiate this, which all of you are used to doing by now. So I'll just write directly. So differentiation of x square is 2x minus differentiation of x to the power 4. That's 4x cube minus differentiation of 2x, which is -2. So this is the derivative. This is what we can call the derivative of the function. Okay. Now second derivative. So this is where the definition applies. It is derivative of derivative or rate of change of derivative. So we have to now differentiate this term. So substitute this here. And once again, when we differentiate, we can see differentiation of 2x is 2. Differentiation of 4x cube is 4 into 3x square. So 12x square. And differentiation of 2 is 0. So this is the second derivative. And similarly, now for the second part, the value of second derivative at the point x equal to 1. It's nothing but we want to calculate the value of this expression when x's value is equal to 1. So that is 2 minus 12 or minus 10. So that's the answer. So talking about the use of second derivative, what do we, so now that we've understood how to calculate second derivative, now when do we need second derivative? Let's understand that. So of course, we're going to see that in analysis of local maxima and minima, second derivative comes into play. But we'll also see before that there are certain situations in physics where second derivative is directly related to the definition of a quantity. So for example, if you have a situation like this, that a particle is moving along a straight line. So a particle moves along the x-axis such that its position x at an instant t is given by some relation, let's say. Okay, so x is equal to, suppose it is 10t minus 4t square, where x is in meters and t is in seconds. Now we want to find its velocity v, its acceleration, and its instantaneous velocity at t equal to 2 seconds. So we want to do all this. So the concept we'll apply over here is that the kinematics definition, which of course we'll come to in a lot more detail when we finish this chapter of vectors. Anyhow, the kinematics definition of motion along a straight line is that velocity is instantaneous rate of change of position. Acceleration is instantaneous rate of change of velocity, which means that acceleration is rate of change of the derivative of position with respect to time. So you can see here how acceleration's relationship with position is a direct application of the concept of second derivative. So we're going to use that concept over here in this question. Let's work this out. Very good. Yes, that's correct. Just have to give the unit also. Okay, so since now we are dealing with physical quantity, we have to also give the answer in the proper unit, right? Okay, very good. That's correct. So let's confirm the answers. Okay. So x being 10t minus 4t square, instantaneous velocity is instantaneous rate of change. So we have to just differentiate this, but now the variable is t. Okay, x is the dependent variable and t is the independent variable. So we are differentiating it with respect to time. So this is our instantaneous velocity as a function of time, where this velocity is in meters per second and the time is in seconds. Right. So the second part, our instantaneous acceleration becomes dv by dt, or we can also say it becomes second derivative of x with respect to time. So the minus sign just shows that the direction of acceleration is along the negative x-axis. So notice one thing, that this is a uniform, what we say, deceleration, because it is a negative acceleration. And uniform because it's not varying with time, whereas this is a variable velocity because it's changing with time. So now coming to the third part, the instantaneous velocity at t equal to 2 seconds will become 10 minus 8 into 2. So v will become minus 6 meters per second. So this shows that the magnitude of the velocity is 6 meters per second and direction is along negative x-axis. Okay, so I'm not using the vector notation here because it's a one-dimensional or motion along a straight line. But nonetheless, the velocity does have a significant direction here. It is either along the positive x direction or negative x direction. And just the algebraic sign of the value of v tells me the direction. We don't need the unit vectors I cap, j cap, and all that, okay, because it's a motion along a straight line only. Okay, so very good. All of you have got the answers correct. So as you can see, it's pretty simple. So now we come to the important thing here, that why second derivative is important for us in analysis of functions. So we will see local maxima and minima. Back to that. But by what we call second derivative analysis. So there's something quite interesting here. So the idea is, if you look at the behavior of the derivative of a function at a point where the function reaches a local maxima, you'll realize something very interesting, that the derivative at the peak point is changing from precisely at the peak point we have seen before, that the derivative is 0. So the slope of a tangent drawn here is 0. But as we discussed earlier, if you draw a point before this, at a point like a minus delta x, slightly before this, okay, the derivative has a positive value. And if you draw a point just after this, the derivative has a negative value at a plus delta x. So we'll come to the minima point also, but let's focus on the maxima point first. So what we can see here is that if the function has a maxima at the point A, that is local maxima, can see that the derivative of the function is 0 at the point A. That is, slope of tangent at x equal to A is 0. But the derivative is positive at A minus delta x. And the derivative is negative at x equal to A plus delta x. So what we can see therefore is the behavior of f prime x, that is the derivative, is such that it switches from a positive to negative value at x equal to A. So therefore the derivative itself is decreasing in nature at the point x equal to A. So if the derivative is decreasing, that means the rate of change of the derivative or second derivative should be negative at x equal to A. So in other words, f double prime of A should be negative. So let's understand that visually over here. So along with this function now, if I was analyzing the derivative of the function, so what I would notice about f prime x's behavior at the point E. So this is now the analysis of f prime x versus x. So what I would see is at precisely at the point A, okay, the derivative's value would be 0. But before A, the derivative's value would have been positive. Because here you can see the slope is positive at A minus delta x. And after A, the derivative's value would be negative. So the derivative must be having this kind of a shape. Okay, so if I'm looking at f prime x is such that it is positive at a point before x, before A, it is 0 at A, and then again it's becoming negative at a point after A. So that means f prime x has a negative slope at the point x equal to A. So that only shows us that the second derivative should be negative at the point A. So just note down this point first, then we will look at the maxima kind, sorry, the local minima kind of point, and we'll see that it has an interesting application there also. Okay, so if there's any doubt regarding this point, please let me know. Okay, now similarly, if we turn our attention to the dip point, okay, where there is a local minima, we'll again see there's an interesting behavior of second derivative at that kind of point. So now let's say I'm more interested in this point where the tangent has again become flat, okay, but such that if I take a point before this, the slope of the tangent is negative. If I take a point after this, the slope of the tangent is positive. So at B, there is a local minimum. Okay, so if fx has a local minima at x equal to B, we can see that f prime x is equal to 0 at B. Slope of tangent is 0 at x equal to B. But f prime x is negative for x less than B, and f prime x is positive for x greater than B. So therefore, we can see that the behavior of f prime x at x equal to B is such that its value switches from negative to positive at x equal to B. So that means f prime x, the derivative is decreasing at x equal to B. Okay. So once again, you can see here that at the point B, f prime x will be 0. But before that, it will be negative, and after that, it will be positive. So f prime x at the point B has a negative slope at x equal to B. Or say that f double prime at the point B should be negative. Oh, sorry, my mistake. It's going from negative to positive, so it's a positive slope. So the, the value of f prime x is changing from negative to positive, no? So it's increasing. It switches from negative to positive. You can see it's going from negative to positive, so it's having a positive slope. So this is the condition. So now you can see the contrast that for local maxima above that we saw, we had the condition that derivative should be 0. Okay, and we had the condition that second derivative should be negative. This was a condition for local maxima. Now similarly here we are seeing the condition for local minima is that the derivative should still be 0, but second derivative should become positive. So that's how they're different in terms of the behavior of second derivative.
So,
Yes.
but when the derivative is zero, if we differentiate the derivative, then we'll get zero only. No?
No, beta, function just because it has a value 0 at a certain point doesn't mean its derivative is 0. No? You understanding? For example, if we have the function, just a minute. If we have the function, let's say x cube minus x square. Okay. So what is the derivative of the function? It's 3x square minus 2x. what is the second derivative of the function? It is 6x minus 2. Now you can see that dy by dx is equal to 0 at the point x equal to 0. You can see. But what about second derivative at this point? Is it 0? No, no, it is minus 2.
Yes.
You're following the point?
Yes, I got it.
Or another example is you take a function sin x. So what's its derivative? Its derivative is cos x. Okay. Now you can see that fx is 0 at x equal to pi, 0
Zero.
or even pi for that matter. Okay. But what about f prime x? F prime x is not 0 at pi. Okay. F prime x is minus 1 at x equal to pi. It is plus 1 at x equal to 0. Okay. So just because the value of a function is 0 at a point doesn't mean that its derivative has to be 0. Okay. So just like that, if the value of the f prime is 0 at a point, it doesn't mean that f double prime will be 0. Now, f double prime may still be positive or negative, and that is the meaning of it. That if f double prime is positive at a point, that means the slope is increasing at that point. F prime is increasing. So if it's 0 exactly at b, but it's increasing in nature, that means after b it should become positive, and before b it was negative. Understood? No? So that's why the function is going through a dip point over there. Is
Yes.
it clear?
Yes, sir.
Oh, good. Okay, so if we put this information together, we can see that we can develop a step-by-step method for find maxima or minima for a given function. Okay, what we do is, first step, find the derivative of the function. f prime x. Okay. Find the second derivative of the function. By differentiating the derivative, which is f double prime x. Okay, so we do this. Then second step, we find what is called the critical points. That is, these are the values of x at which the slope equals to 0. So they are basically local maximas and local minimas. So those are the points where the slope of the tangent becomes 0. So critical points, how do we calculate? They are basically roots of f prime x equal to 0. So we solve this equation for critical points. Okay. Now there can be any number of maximas and minimas like this. So each of these critical points, let's say x1, x2, x3, so like this. Just find them out. And then finally, the third step, we analyze these critical points for understanding whether a particular critical point is a point of local maxima or a point of local minima. So that we call as the second derivative test. So we test these points using the second derivative. Okay. So at each critical point, okay, we find the value of the second derivative. Okay. And we understand that if the second derivative is positive, then it means that there is a local minimum. And if the second derivative is negative, that means there's a local maximum. Okay, so this is the general method. We will apply it to some example questions, and you'll see that this really makes the analysis very easy. Especially in comparison to the whole number line method that we were discussing in the previous couple of lectures. Okay, so let's apply this to a particular function and understand the execution of this method. So suppose we have something like this now, y is equal to we want to find local maxima and minima. So we just apply these methods. So step one, given that the function is this, find the derivative of the function, which is going to be differentiation of this. So that's 6x minus 3x square. Sorry, that's it. Okay. Or we can further factorize it and write this as 3x into 2 minus x. And second derivative will be differentiation of the derivative. So that will become 6 minus 6x. Or we can write that as whatever, minus x. Okay. Now, second step, critical points we want to find out. Sometimes critical points are also called turning points because the behavior of the function turns. Okay. So if you hear the term turning points, it means the same. So turning points are the roots of this equation, that f prime x is equal to 0. Or so in this case, we can see that we are getting two critical points. These are our two critical points. So typically you can visualize that two critical points will either mean that the function looks like this or that the function looks like this. So either at 0 it's having a local maxima and at 2 it's having a local minima, or at 0 it's having a minima and at 2 it's having a local maxima. We still have to figure out which of these two is happening. So for that we have the third step, which is the chain rule step. Sorry, not the chain rule step, but the second derivative test. So let's start with the first critical point at x equal to 0, f double prime of 0. Now what is that? That is 6 into 1 minus 0. So that's positive. So that means the function has a local minimum at x equal to 1, and its value is f of, sorry, at x equal to 0. It's not, and its value is f of 0, which you can see from above is plus 2. Okay. So this point 0, 2, this is the dip point in the graph. So just make a note up to here, then we will discuss about the second critical point, which is x equal to 2. If you've reached this step of second derivative test, you can check out yourself that when you analyze the second derivative at this critical point, x equal to 2, you'll get the value of second derivative to be negative, which means that it's a local maxima kind of point.
So what should we do when the derivative consists of trigonometric ratios and all?
You mean if dy by dx is some trigonometric function?
Like it also has trigonometric ratios in it. A combination of logarithmic function and trigonometric function.
Yeah, then like finding the critical points becomes a little more difficult, but nonetheless it's the same method. Okay.
So how should we do that?
Sorry.
How to find the critical points in that case?
You just have to solve the equation. So for example, if your derivative of the function is coming out to be like x plus sine x, so for the critical point you have to solve for the equation that x plus sine x is equal to 0. So you have to find such a value of x where x itself is negative of sine x. Okay.
Okay, sir.
But see, those kind of transcendental functions are not going to be important for us at the physics level. So you need not worry about that at this stage. Okay. There are some advanced equation solving techniques and all which are used for solving those kind of equations.
Yes, sir. So when we'll be doing those, we'll come to know.
You might be doing something like that in advanced calculus in maths, but again, transcendental functions, roots and all that are not something which is like very straightforward. It's quite advanced in mathematics. Okay. So don't worry about transcendental functions for maxima minima. Of course, we will look at functions which are purely trigonometrical, and for them it's quite easy to find critical points.
Yes, sir.
Okay, so let's go ahead and analyze the second critical point also now. So the second critical point you can see is at x equal to 2. The value of the second derivative will become 6 minus 6x. So that is 6 minus 6 into 2. So that is minus 6. You can see that it is negative. So that means the function has, as expected, a local maxima at the point x equal to 2. And the local maxima's value at that point is the y coordinate, which is f of 2. So the function itself was 3x squared, so that will become 3 into 2 square minus x cube, so that is 2 cube plus 2. So this will become 12 minus 8 plus 2, so that's 6. So that critical point now will have coordinates 2 comma 6. This will be a peak point. So with this information now, for example, we can analyze how the function's graph looks, even without drawing all those intervals and making a number line and all that. By just sort of estimate like this, that we can see that is 0 comma 2 is a dip point for us. And then again, say 2 comma 6 is going to be a peak point for us. Okay. Now we can also see that the function is 3x square minus x cube plus 2. So what happens is that for x tending to minus infinity, y tends to infinity because the minus x cube term dominates. So the function will be like this. And similarly, for x tending to infinity, the value of y will tend to minus infinity because again minus x cube term dominates. So you can see that this particular function, it has a domain, the natural domain, that is minus to plus infinity. So accordingly, the range is also minus to plus infinity. So it's going the other way around, that when x is negative infinity, y is positive infinity and vice versa. Okay. But it also has local maxima equal to 2 at the point, sorry, equal to 6 at the point x equal to 2. And local minima equal to 2 at the point x equal to 0. Okay. So now just using the analysis of local maxima and minima, you can see that we have done this full analysis. We didn't have to find the intervals in which f prime was positive, negative, solved by wavy curve method and all that. It was not necessary over here because just this simple trick of second derivative test directly gave us local maxima and minima. And from that and a bit of analysis about how the function behaves when x is plus or minus infinity. So these two things put together, giving us a precise method of finding out the behavior of the function as well as the particular points which are the local maxima and minima.
Sir, can you tell how to find the domain and range again? From this method.
So,
Yes.
can you please summarize this example once again briefly?
Yeah. So you can see that we are just applying this second derivative test method. Okay. So given any function, the first step is we find out the derivative of the function and second derivative. Then next thing is we find the critical points by finding the roots of the equation f prime x is equal to 0. So we find all these sort of points where the derivative is 0. And then we apply second derivative to each of these critical points. If at a particular point second derivative is positive, that means it is local minima. If it is negative, it is local maximum. Okay. So now you can see that we will just be applying this step-by-step process to the particular example below. So I've worked out each of the steps in just a moment. I've worked out each of those steps in that same order, and you can understand how You got that? Okay.
Yes, sir.
First step, you find out the derivative, and you find out the second derivative. Then second step, you find out the critical points. And then, so we saw there are two critical points, x equal to 0 and x equal to 1. So then we worked out the second derivative test at each of those critical points. Okay, so that is this step. So from that we found out that, okay, x equal to 0 is the local minima point and x equal to 2 is the local maxima point. So when x is equal to 0, the value of y you can see from the function. You put the value of x as 0 in the function, so the value of y is 2. So that 0 comma 2 is the point where the local minima exists or the dip point exists. Similarly, for x equal to 2, there is a local maxima. And when you put x equal to 2 in the function, the value of y comes out to be 6. So 2 comma 6 is the coordinates of the peak point. Okay. So that gives us an idea about how to draw the graph.
Yes, sir.
Additionally, for the analysis of the graph, we are also using this, that when x is a very large negative number, y will be a very large positive number because we have this term minus x cubed. And similarly, when x is a very large positive number, y will be a very large negative number. You can try this out by taking a large number like a million or something like that. So take the value of x as minus 1 million. You'll see y will tend to plus infinity. And take the value of x as plus 1 million. And you'll see y will tend to minus infinity.
Yes, sir.
Right. So that is what is telling us about the range of the function. Domain, though, we can see the natural domain will be all real numbers because there's no restriction on defining y as a real number. There's no value of x for which y cannot be defined as a real number. So there's no problem with range or domain for that matter. Okay, so in this case, you can see that local maxima and minima is not really affecting the range of the function because the function is going unlimited from plus infinity to minus infinity, as x is going from minus infinity to plus infinity. Okay, so just it will take you a little bit of practice to get used to applying this method, just like we've practiced chain rule earlier and things like that. So let's look at another example. So this one you try out yourself now. So we have the function x belonging to all real numbers. So first of all, analyze the function and find all critical points. Then find the local maximas and minimas. And then also analyze about the range of the function. So just try this out, people. Okay, so Rohan and Bhavik, I'm just going back to the previous question to answer your questions once more. So Rohan, you have asked how the second derivative came in the previous question. So second derivative comes by differentiating the derivative. No? See, in the previous question,
Yes, sir, I got it. That.
you got that, no? Okay,
Yes,
so,
yes.
so you got this one by default. Okay. And Bhavik, you have also
Sir, I didn't ask anything.
Bhavika, sorry, my mistake. You asked that question. Okay. So all of you are clear about the previous question now. Okay, so let's come to this. So what are the critical points that you all have got for this question?
0, root 2, and minus root 2.
0, root 2, and minus root 2. Very good. That's
Yes.
correct. So now obviously we have three critical points, means either two of them are maximas and one is minima, or inverse of that two of them are minimas and one is maxima. Yes, very good. The answers I'm getting are correct mostly. Okay. So given the function 4x square minus x to the power 4 plus 1, the derivative of the function is eight x minus 4x cube. So I can take 4x common. So that is 4x into root 2 minus x into root 2 plus x. That's the derivative. And second derivative will become differentiation of f prime x. So that is differentiation of this term, 8x minus 4x cube. So that is 8 minus 12x square. So this is the derivative and this is the second derivative. Okay, so now critical points. They are the roots of the equation f prime x is equal to 0. So from this you can see that x equal to 0, x equal to minus root 2 or approximately 1 minus 1.41, and x equal to root 2 or approximately 1.4. And so these are my three critical points. So now we analyze for local maxima and minima. So at x equal to 0, f double prime of 0 is basically what it is, 8 minus 12 into 0 square. So that is 8. So it is positive. So fx has local minimum at x equal to minus root 2 is 8 minus 12 into minus root 2 whole square. So that is 8 minus 24. So that's minus 16. So it is negative. So that means the function has local maximum. I'll come to the values, but first let's just analyze. Okay. And at x equal to root 2, you'll see it's the same thing. Second derivative is negative, means that again the function has a local maximum. So it has two maximas and one minimum. Okay, so far this is what we've understood, that x equal to 0 point is a minima and x equal to root 2 and minus root 2 are the points where the function has a maximum. So now we can understand that the function's shape must be something like this. The graph must be something like this: minus root 2 and plus root 2. Okay, now having understood this, just a little bit. Yes, very good, Kirti, that's correct. Now we have to just find the values. Okay, so we can see that for the local minima, at x equal to 0, the value of y becomes what? Now, what was the function? Remember, the function was 4x square minus x to the power 4 plus 2, right? Yeah, 4x square, sorry, plus 1, my mistake. So this was the function. So it is f of 0. So that is 1. Okay. So 0 comma 1, this is the so-called dip point. Okay. Whereas the local maxima at x equal to minus root 2, for example, the y coordinate is f of minus root 2. So that is 4 into minus root 2 squared minus of minus root 2. So actually that minus sign doesn't make a difference because it's an even power, but anyhow, let's try this. So minus root 2 to the power 4 plus 1. So this is becoming 8, right? Minus 4 plus 1. So it's becoming 5. So this is one of the peak points. And again, so when you do this whole calculation, you will see this will again come out to be 5. So that's another peak point. So we have one dip point in between and two peak points. Okay. And also now you will understand that y tends to minus infinity as x tends to minus infinity or x tends to infinity, because the function has a x to the power 4 term. So this term dominates for x tending to plus minus infinity. So you can think in terms of number line what is happening now. 0 minus root 2 plus root 2 has to come from a very large negative value to this peak point here, then this dip point, then this peak point, then like this. So now this visualization of the graph will also help us understand the range of the function. This time the range of the function will not be all real numbers, because the function starts from negative infinity, goes up only up to a peak, then again comes down, then again goes up to only a peak, and then again goes down to minus infinity. So it doesn't go to plus infinity. So it has a limited value of the upper limit of the range. Or in other words, it has a non-infinite global maximum.
So can you explain the range part again?
Yeah, we'll do. For that, we still have to understand the graph first. But have you understood this part that I've written below, that y tends to minus infinity for both these things when x is plus infinity or minus infinity? This thing you understood?
Yes, sir.
No, because this minus x to the power 4 term will dominate. No? So if you put together this information now, this piece of information that we have along with these, okay, then you'll understand how to get the value of the range. Okay, so if you put together this information now, we can see that the nature of the function, apart from the fact that it's a very symmetrical kind of function because it has only even powers of x, but also, so if this is minus root 2, this is root 2, then we saw that the two peak points were having y coordinate of 5 each, right? Let's say this is one of the peak points and another peak point. And the dip point was having a y coordinate of 1. Whereas when x is tending to plus or minus infinity, y is tending to minus infinity. So the function has to have this kind of a shape. It has to come from minus infinity, peak at this point, then drop, dip at this point, then again peak at this point, then again drop and go to minus infinity. So now you can see that for the entire domain, of real numbers, minus infinity to infinity, y's lower limit is minus infinity. Okay, but upper limit is never going beyond this peak point, so it's never going beyond 5. So you can see that y never exceeds 5. So this is the range. So you can see that apart from the fact that it has local maxima equal to 5 at x equal to root 2 and again repeated at x equal to minus root 2, and the fact that it has local minima equal to 1 at x equal to 0. But apart from this, it's also that this is also the global maximum. So global maxima is 5, whereas global minima is tending to minus infinity. Okay, which you can see in the range itself. It's going from minus infinity up to 5. So is it clear now how we got the range from this same analysis about maxima minima only?
Yes.
Okay, now a couple of doubts remaining from the revision worksheets earlier. Rohan, I think you had something from the
Yes, sir, I have some doubts. Sir, the 17th sum I'm not getting.
17 sum. Okay, we'll discuss about that. Okay, so I hope that question was clear. I'm just going through the chain rule worksheet, question number 17, right? So just think of this like some variable, like let's say y is a function of time. So this is y is equal to t raised power 6 into square root of 5t square minus t. Okay. So this is some kind of function. Now you can see that this is the product of two functions, and the second one is this thing. It's a composite function. So it is like, let's say, h of t multiplied by f of t, where f of t is a composite function, which is square root of 5t square minus t, and this h of t or anything else we can call it whatever. This is a simple function. This is t raised power 6. Okay, so Rohan, clear up to this?
Yes, sir.
Okay, so now I want to find dy by dt. So I'll use product rule first. Okay, so it will become differentiation of h into f plus h into differentiation of f. Okay, now differentiation of h is very simple. It will just become 6t to the power 5, right, into f, which is square root of 5t square minus t. But this second term is a little complicated, so we'll have to work this out separately. So what we'll do is we'll use chain rule now here separately, that ft is square root of 5t square minus t. So I can write f is square root of z, where z is equal to 5t square minus t, right? So f prime will become df by dz into dz by dt. Okay, is it clear up to this step?
Yes, sir.
Okay, so now f is what? Root z. So uska derivative kya hoga? 1 by 2 root z, right? And z is how much? It is 5t square minus t. So its derivative will be how much? 10t minus 1. Okay, and then just put the value of z. So we will get this f prime Okay, we'll get f prime as 10t minus 1 in the numerator divided by 2 root z. So that is 2 times square root of 5t square minus t. So I'll substitute this value of f prime that I got here. I'll put it here. Okay. So this term is coming from here. So this is 10t minus 1 in the numerator divided by square root of 5t square minus t. So as far as differentiation is concerned, now we've got the answer, but we might want to take LCM and all that. So to simplify this, it's a little bit more lengthy. You will take the LCM, which is square root of 5t square minus t. And when you take the LCM, you can see this term will just become 6t to the power 5 into square root of this into square root of the same thing. So just 5t square minus t plus this term will become 10t to the power 7, right, minus t to the power 6. And then just open this bracket in the numerator and just simplify it a little bit more and you will get the final answer. So finally, this is your derivative. This is your dy by dt. So what made this question lengthy was that not only chain rule, but we are having to use product rule and chain rule in the same thing.
Okay, sir.
So just go through the steps once and let me know if everything is clear, right?
Sir, even I have 2 doubts.
Can you just speak a little bit louder? I could not hear you.
Sir, even I have 2 doubts. One is
Yeah,
the second one, and the other one is from the
8th one, no? Is the message you just sent, Bhavika? 8th question in
yes,
product rule?
yes,
Yeah, and the other one is?
32nd.
Okay, okay. Anything in this assignment, the chain
Yeah.
rule assignment?
Yes, sir. 32 one is from this assignment only.
32 from this. Okay, so we'll do that one first, then we'll go back to the other assignment.
Okay, sir.
So,
Yes.
so but you missed out the 2 into square root 5t square
Oh, I
minus
missed
t.
out the 2, is it? Correct.
Yes.
So there should be 2 over here. No? Okay. So I can put the 2 here. Okay. Later that 2 will come here, but this will become 6 into 2. Right. So this coefficient here should become 12. Right. So it's correct now. Just check.
Yes, sir.
It's
It's
correct.
Thank you, sir.
Okay. So this will become 60t to the power 7 plus 10. So 70t to the power 7. Okay. Then there's a minus 12 minus 1. So minus 13t to the power 6 kind of term divided by this. Okay, so I'm removing this because I've sent the solutions also. So I think the steps should all be there in that. Okay. Bhavika, question number 32, right?
Yes, sir.
Okay, so let's come to that. So where in this interval the function is increasing and decreasing. Okay. So basically we are already given an interval x greater than equal to -1 and less than equal to 20. But now this interval has to be broken into sub-intervals for which this function is increasing and decreasing. Okay. Now overall, we can see one thing, that as long as the term inside ln does not become negative, y is defined. And that's going to be okay because we are taking x. Okay, we are not taking x smaller than -1. So when x is -1, for example, this term is -20 plus 1 plus 100. Okay, so there's no problem. So we don't have to worry about the function not being defined for any point in this. So this is part of the domain of the function. So this is like a specific domain. This is not the natural domain. the natural domain will be even larger. Okay, so now we have to just find out that where f prime x is positive, the function is increasing, and where f prime x is negative, the function is decreasing. So the function itself is what? It is natural log of x to the power 4 plus 20 x cube plus 100, or I can write it as y is equal to ln z, where z is equal to x to the power 4 plus 20x cube plus 100. Okay, so I can see that by chain rule now, dy by dx, which is basically f prime x, will become dy by dz into dz by dx. So dy by dz is 1 by z, because ln z's differentiation is 1 by, and dz by dx is the differentiation of this polynomial function. So it will give me a cubic polynomial function, right? So 4x cube plus 20 into 360 x square, and 100 is a constant which is. Okay, so now I'll just shift to this side. So you can see that f prime x is becoming how much for us? F prime x is becoming, we can take 4x square common, right? So it is 4x square into x plus 15. Okay, divided by z, and z is this term. Z is x to the power 4 plus 20x cube plus 100. Okay, so now you can see that in the interval that is given to me, the denominator is always positive because x is greater than -1. So in this interval now, what is happening? The denominator is always positive. X to the power 4 plus 20x cube plus 100 is greater than 0 for all values. Okay, so that means f prime x is positive for the numerator being positive, and it is negative for, again, the numerator being negative. Okay, now the numerator is also, see, it's x square is a non-negative term, no? So basically we are dependent on x plus 15. So the condition for x plus 15 to be greater than 0 is that x is greater than -15, and the condition for x plus 15 to be negative is that x should be less than -15. So this is actually falling outside this domain.
Yes, sir.
So that means for this entire part, only one condition is satisfied, that f prime is positive. So finally, what is the conclusion? That in this entire domain, the function is only increasing. It's never decreasing.
Okay, sir.
Right? No, this is clear about that. So it just looks like a very complicated function with that ln and all that. Okay, but luckily for us, we have taken the domain from -1 onwards. So the denominator is always remaining positive, and the numerator is already factorized, so it's very easy. Okay. So hope this question is clear, beta.
Yes, sir.
Okay, very good. Okay, so we'll move on to the question number 8, which you have asked. But wait a minute. Before that, Kirti has asked question number 10 of the same worksheet. So before I switch worksheets, let me just go through question number 10. Tan inverse, na? Yeah. You remember that last time I had told you how to deal with this inverse trigonometric function type of things. Okay. So if u is equal to tan inverse of 3t minus 1, then I'll just first apply this step that I'll take tan on both sides. So tan of u must be 3t minus 1. Now this becomes easy. Okay. So differentiation of tan u with respect to u or t should be equal to differentiation of 3t minus 1. Now this we'll have to apply chain rule because we have tan of u and we are differentiating with respect to t. So this will become differentiation with respect to u of tan u multiplied with du by dt. And right hand side is very simple, it's just becoming 3. So this is the chain rule step. This is the critical step. Is this clear, Kirti, so far?
Yes, sir.
Okay, very good. So once this is clear, rest is now just recall the formula of differentiation of tan u. It's sec square
X
u
square u.
du by dt So just a bit of work remaining now, that we have to express du by dt in terms of u. Sorry, in terms of t, not in terms of u. So what we'll do is we'll express this as using the identity which we know, tan square u, and then we'll go back to resubstitute. The tan u is this, so that means du by dt becomes 3 upon 1 plus tan u's whole square, that is 3t minus 1 whole square. And you might just want to expand the term in the denominator, just express it as a quadratic function of t. So this is becoming my du by dt.
Yes, sir.
Okay, so this is also clear. Okay, so this is also there in the solution, so I'm not asking you to note this down. Okay, I will just switch now to the other worksheet.
So I had a doubt in the same worksheet.
Oh,
This
okay,
is-
just a moment. I'll come back to that. Wait. Chain rule, product and quotient rule. Yeah. Yeah, question number 8 of this, right?
Yes, sir.
So this is like, one of those very manipulation based type of questions. So one just has to get used to this type of question, nothing else. Okay. So see fx, so I'll just write it as f is given as x cube g. Okay. And we have to find the value of f prime derivative at x equal to -7. Okay. So now what we'll use is we'll use the quotient rule here. So df, sorry, the product rule here. df by dx is going to be d by dx of x cube multiplied with gx, right, plus x cube multiplied with differentiation of gx,
Yes, sir.
right? So this step is clear now? Okay, so now, so I can directly write this as f prime x is equal to 2x square, sorry, 3x square, my mistake. Yeah, 3x square into gx, right, plus x cube into g prime of x. Okay.
Yes, sir.
So what is f prime of 7? It should be 3 into or whatever minus 7. F prime of -7 is nothing but the value of this above expression for x equal to -7. So it is 3 into -7 squared g of -7 plus -7 cube into g prime of -7. Okay, clear up to this step now?
Yes, sir.
Now we have to just substitute. See, g of -7 is given to us as 2. G prime of -7 is given as -9. Okay. So this is becoming 3 into 49 into g of -7, which is 2. Okay. Plus this will become 49 into 7. So that's how much now?
343.
280 plus 63 now. So that is 343. Is it? Okay. So this is minus 343 because it's -7 cube into g prime of -7. So g prime of -7 is -9. Okay. So this becomes the value of f prime of -7. So it's just, a lot of manipulation in the question, nothing else.
Yes, sir. Understood.
Okay, so shall I clear this now?
Yes, sir.
Okay. Yeah. Now What was the other doubt? You had somebody in question number 30 now
Yes, question number 30 of the chain rule assignment.
of the chain rule one. Okay.
I could do the differentiation, but I did not understand even the solution how to determine whether the object is moving towards the right.
Okay, just a moment. Yeah. Sorry, which question was it? 30. Okay.
Yes, the question number 30.
So now in this we have object is moving. Acha, you are asking about this kind of thing. So determine where in the interval the object is moving towards the right and where it is moving towards the left. So moving towards the right means v should be positive. Okay.
Yes.
And v is what? ds by dt. And moving towards the left means v should be negative. Okay. So let's start with s. So s is sine. So this is going to be quite complicated because you're taking an interval like this, no? Okay. So ds by dt or v is becoming 3 cos 3t minus 2, correct?
Yes, sir.
Right?
Yes, sir.
So now the condition for v to be greater than 0 is basically what? That cos 3t should be greater than 2 by 3. And the other one for v less than 0 is that cos 3t should be less than 2 by 3. Okay. Now see, when we are taking the interval of t as 0 to 3, now we can think of this like this, that cos theta is greater than 2 by 3 and cos theta is less than 2 by 3. So how do we solve this inequality where theta is basically what? Theta is 3t. Okay. And t is in this interval. T is in the interval 0 to 3. Now you have to understand that this is SI unit. So this theta is in radians. So theta is going from where to where? From 0 to 9 radians. You understanding my point, beta?
So can you explain this step just before?
Yeah. So are we clear up to this step? This
So
step?
the 2 by 3 part, can you explain that again?
Yes, sir. The same.
2 by 3 how we'll explain na? See, v का formula आ गया ना? V is 3 cos 3t minus 2. So for v to be positive, 3 cos 3t minus 2 has to be greater than 0, no? So from that we'll get this, no?
Yes, sir.
Okay, understood now? Now all I'm doing is I'm replacing 3t with theta. Understood my point? So
Okay.
this directly becomes that cos theta is greater than 2 by 3 and this becomes that cos theta is less than 2 by 3. But what is theta itself? It is 3t. Now, so are you clear up to this?
Yes, sir.
Yes, sir.
Okay, now the thing is how do we solve for t? So I'm just switching. Just a moment. Okay. So this kind of analysis is like the one which I was telling you that it's little tricky. Okay. Anyhow, discuss. Okay. Yeah. So now remember what kind of equation we were solving. We are solving this kind of equation that cos theta, for example, I wanted to make be greater than 2 by 3, where theta is equal to 3t. So as t is going from 0 to 3, what is happening? Theta is going from 0 to 9. But this is radians. Okay. So remember that 9 radians is basically equal to how much? It is little bit greater than or little bit less than 3 pi. Slightly less than 3 pi, but greater than, for example, 2.5 pi. Got it, no?
Yes.
Because pi is 3.14, no?
Yes, sir.
Okay, you understanding my point? So now see, we have to visualize the cos theta graph. Okay. Between about 0 and 9 pi, if we visualize, then we should be able to estimate the solution. Okay. So this is cos theta versus theta. So that graph will be something like this. This is where we complete 2 pi. And this is where we come to 3 pi. Oh, sorry. 3 pi by minus 1 हो जाएगा. This is 5 pi by 2. This is where we come to 3 pi. So I need not go beyond 3 pi because anyway I'm analyzing theta for 9 radians, which is slightly less than 3 pi. Okay. So my actual domain in terms of theta will be somewhere over here. This is 9 radians. Okay, and this is 0. So between this and this. Okay. Now we know that this value is plus 1. This value is minus 1. So my 2 by 3 point will be somewhere here. Okay. So what I have to do is I have to draw a line like this. Okay. And we will see that there is some value which is, let's say, alpha over here, some value which is beta over here, and some value which is, let's say, gamma over here. So this condition now in the graph, you can see that cos theta is greater than 2 by 3, which was my condition for V to be positive, is satisfied for theta being between 0 to alpha, okay, union with beta to gamma. You understanding my point, beta?
Sir, I did not understand the purple part.
See, this is a line 2 by 3, na? So I want cos theta to be greater than 2 by 3. So wherever it cuts the graph, now this part, in this part of the domain 0 to alpha, the value of cos theta is greater than 2 by 3. Na?
Yes, sir.
Understand?
Yes, sir.
So
Yes,
in
sir.
the first quadrant, na, there must be some angle alpha less than 90 degrees at which cos theta is equal to 2 by 3. So what is alpha? Alpha is cos inverse 2 by 3 in first quadrant. Okay. Now, if you use a scientific calculator, you will see that that value of alpha comes out to be, okay, so 2 divided by 3, its cos inverse comes out to be about 48 degrees. So alpha is approximately 48 degrees, which if you convert to radians, it will become nearly, something slightly greater than pi by 4. Actually, it's slightly greater than 45. No? So you can say that alpha is slightly greater than, so it's almost equal to pi by 4 or 45 degrees. Okay. So now what will beta be? Now see which quadrant beta is in. This is our pi. So this is our 3 pi by 2. So beta and gamma are both in which quadrant? In the fourth quadrant.
Fourth quadrant.
The beta is in third quadrant and gamma is in fourth quadrant. Understood now? So beta's value, so if I took this more or less as pi by 4, then beta's value would be how much? It would be 3 pi by 2 plus pi by 4 almost. Or more precisely, it would be 3 pi by 2 plus alpha, where alpha is this thing, cos inverse 2 by 3. And similarly, gamma would be, now this point is, no, wait a minute. This is alpha, no? So it should be 2 pi minus, okay, sorry. It's not this. This is 2 pi minus alpha. Okay. So it is nearly 2 pi minus pi by 4. That right. And similarly, gamma, this would be 2 pi plus alpha. So now this is the values of theta, and you have to just replace theta with 3t. So from that you will get the values of t. You understanding?
So it's a little bit confusing.
Sorry, a little louder, please, beta.
So it's a little bit confusing.
Yeah, it is a little confusing. But it is like advanced trigonometry. Okay, so you will get used to this more in mathematics, okay, than in physics. So just analyze this later once more. Okay, so I'll just put up the solution now. So for example, if theta belongs to 0 to alpha, okay, that means, so 0 to alpha like this, that means 3t belongs to 0 to alpha. Okay. So that means t belongs to the interval 0 to alpha by 3. So basically this is t is greater than equal to 0, less than equal to, now alpha was what? It was cos inverse 2 by 3 ka 1/3. So it is nearly, so this term is going to be nearly pi by 12 because cos inverse 2 by 3 is nearly pi by 4. So that is giving you the first part of the domain where your V is positive. And the next part of the domain is between beta and gamma. And again, beta and gamma are like this. Beta is 2 pi minus alpha and gamma is 2 pi plus alpha. Okay, is this clear? Okay, is this clear, beta?
So the one which I've written in blue color, it's, I'm not getting that.
Which one? Beta and gamma.
Yes, the beta and gamma part.
Beta and gamma देखो कैसे है ना? See, this is like relationship of cos graph. Na? If you compare cos in first quadrant with cos in fourth quadrant, see, this beta is a point between 2 pi and 3 pi by 2. Na?
Yes, sir.
So if you have a value which is common, na, here and here, what is that relationship? This is the relationship, na, that if this is theta, then here this should be theta. Got it, na? So if this value is alpha and this value is beta, then what should be beta? Beta should be equal to 2 pi minus alpha. That's, for example, how we get the relation, na, that cos of, for example, 330 is the same thing as cos 30. Na?
Yes, sir.
Or, for example, cos of 315 is the same thing as cos 45, right?
Yes, sir.
So that's the relation between beta and alpha. Now, similarly, gamma is the next one after this. So actually, after this, you're coming back to first quadrant. Na? Between here 2 pi and this point, which is 5 pi by 2, you're back to first quadrant. So that is why if this is alpha over here, this should again be alpha, na, from 2 pi to gamma. So that means gamma is 2 pi plus alpha. Na?
Yes, sir.
Yes.
Understood? Na? So in degrees, for example, in degrees, if alpha is 48 degrees, it means beta is 360 minus 48 degrees. Okay. And gamma is 360 plus 48 degrees. So then you convert this to radians. And once you convert it to radians, you put it in this equation. So you get the values of time. Is it clear now?
Yes, sir.
Okay.
I'll study the solution. If I'm not still understanding, I'll ask you.
I'll be sending you this worksheet also. So I mean, so this PDF. So just study it once. If you have difficulty with it, you can discuss with me. You can even discuss with your maths teacher if you're doing trigonometry, because you know you'll be doing things like this more in trigonometry in the future. But yeah, once in a while in physics also we get these kind of questions where the mathematics is a little bit complicated, right? So you have to get used to these things, right?
Sir,
Yes.
so finally, how are we going to write that when is it moving to the right?
I showed you, no, in that the
final
values of t I've given you over here. Okay. In that cos inverse term,
that x is less than equal to
that
0.
t is, yeah, like this, like the first interval I showed you, no, that t is between 0 and cos inverse 2 by 3 divided by 3. Now actually cos inverse 2 by 3 in radians is very close to pi by 4. So that second thing, that cos inverse 2 by 3 by 3, I can actually write as pi by 12.
Pi by
So it's
12, yeah.
basically 3.14 divided by 12. If you want to calculate in seconds, it will become like that.
Okay, sir.
Got it now?
Yes, sir.
Similarly, this beta and gamma, you got it in degrees here. So convert that to radians and then just make t as beta by 3 minus to gamma by 3. You know, because 3t is going from beta to gamma. So t is actually going from beta by 3 to gamma by 3.
Okay, sir.
Right? Okay.
Yes, sir. Thank you, sir.
Okay. People will conclude here today. And I've also sent you an additional worksheet just today before the lecture started. So that is based on maxima, minima, and domain range, etc. So try those questions out. We'll discuss in the next lecture.
Okay, sir.
Yes, sir.
So, and for we have a unit test in our school in the month of July. For that, there are
Yeah.
some chapters in physics like which are not done. So, will they be done before the test?
Yeah. There will be, like, which school you're in?
North Point.
Not one. There will be some additional board lecture for that, and you'll have it. Which chapter? Units and dimensions.
Yes, sir.
Yes,
Unit
sir.
and dimensions.
That's a very easy chapter, beta. That's a single lecture chapter. There will be some extra lecture for that will be covered, but that will be for North Point students only, right?
Yes, sir.
Anyway, I think most of you in Yellow House are only North Point students, right?
Yes, sir.
Okay, so
Yes.
that will be covered. Don't worry. That's a very easy chapter. Nothing to worry about.
Thank you, sir.
Okay,
you,
people.
sir.
Bye
Bye,
then.
sir.
Have a nice day. Yeah.
Thank you, sir.